This is another prisoner's puzzle. Here we try to help two prisoners gain freedom through a coin flip game. Okay, here's the situation. They are trapped on an island, and the guard shows mercy toward them and offers the opportunity to gain freedom through a probability game. So each prisoner is provided with a fair coin, that is, head and tail with 50-50 chance, and without prior collusion or any way of communication, each prisoner must independently decide whether or not to use the coin provided, right? So once the decision is made, the guard would collect the coins and will do the following. If only one prisoner uses a coin, the coin will be flipped once, and if shows up in head, then both prisoners will be freed. Now, if both prisoners use a coin, then the guard would flip two coins, and if both land head up, then both prisoners will be freed. Now, if none of them use a coin, then they don't have a chance to gain freedom. So here is the rule. Now, how to help them maximize the chance of gaining freedom? The intuition here is that if one coin is used, then the probability that they're going to be freed is going to be 1/2, because that's the probability where the coin, a fair coin, would be had, right? So for two coins, however, in order for both to show up head, then the probability is 1/4, which is smaller. So ideally, you want a situation where only one prisoner decides to use the coin, right? Then you have better chance, a 50% chance, right? Now, would that work? But no prior collusion or communication is allowed. So in that case, you cannot have a proper way to decide who should bring the coin. You know, who is the leader, who is the master, right? We cannot do that without prior agreement or communication, right? So here, we assume that both prisoners are intelligent and they desire for freedom. And also, by this line of argument, we know that whatever the strategy should be symmetrical. That is, if one guy figured out a way to, try to win the game, try to win the freedom, the other guy must be able to figure that out also, right? So we need some algorithm for that. So with that intuition earlier, we try to have a chance if only one prisoner show up with the coin, right? However, by the analysis here, that cannot be achieved. So with symmetrical decision, maybe it is to their benefit, both just bring the coin. So in other words, each would bring the coin, two coins are present, and the chance of freedom is 1/4, where the guard would flip the two coins and get head and head, right? So would that be the solution? Can we do better? The answer is yes. So maybe this is a probability game. We should consider some probabilistic method. That is, in algorithm, we have what is called randomized algorithm. So instead of bringing the coin, maybe we bring the coin with certain probability for both prisoners. So the P here is a parameter, is a number between 0 and 1. That is the probability that each prisoner would decide to bring the coin, right? So we try to have what is called randomized algorithm. All right, let's do some analysis here. So just review the rules, right? One prisoner brings the coin, then the probability is going to be half. Two prisoners, the probability is going to be 1/4. We know that, right? For them to gain freedom. Now, when we should bring the coin, each prisoner will decide with the probability P to bring the coin. So for that case, with that, the probability that only one prisoner uses a coin is going to be P times 1 minus P plus 1 minus P times P. That is 2P times 1 minus P, right? And then with that probability, there is half chance that the coin will be had, right? So that's the probability of success. Now, for two prisoners both bring the coin, that would happen with probability P times P, that is P squared. Under that, there is 1/4 of chance. So over there, in that case, would be P squared times 1/4, right? So in summary, the chance of success with parameter P is the summation of the two terms, and that turns out to be a quadratic term in P. Now, do some simple derivative, yeah? You know that this value here is going to be maximized when P equal 2/3. And you plug in the value 2/3, and then the chance of winning the game is 1/3, which is better than earlier intuitive algorithm where both just simply bring the coin, right? That would be 1/4 the chance of success. Now here, with our new strategy, the chance is better. So we have a better solution. Now, the question is, how would you do that? Okay, so we know the solution and how to achieve that solution here. So the chance is 1/3, greater than 1/4, right? But each prisoner has to decide to bring the coin with probability of 2/3, right? How to act like that, right? Now here we only have one fair coin, okay? So this is another classical problem in discrete probability where how do you emulate or simulate a biased coin with 2/3 of probability to turn head with a fair coin where there's 50-50 chance of, head versus tail, right? How would you do that? The answer is you flip the fair coin twice, okay? We know that if you do that, there can be 4 outcomes, right? That is, with 2 flips of a fair coin, you would have head-head, head-tail, tail-head, or tail-tail, right? 4 different cases. But we're looking for 2/3 of opportunity here. So what you do is you're going to consider one of them to be invalid state. For example, tail-tail, we're going to reject that, right? So in other words, whenever you have tail-tail, you consider it invalid. Okay, in your experiment, you only accept 3 valid states. That's your sample space. And if you take, head, tail, tail, head as the one that you want to, decide to bring the coin, that would have probability of 2/3, right? So that's the mechanism for the prisoner to decide to bring the coin or not, right? Just do the 2 flips. And then when they see edge, head, tail, tail, head, they bring the coin. When they see tail, tail, they consider that's invalid and gonna redo the experiment, right? So in summary, we have the solution. That is, each prisoner flip the coin twice and would reject TT as a result. In other words, if you see that, just ignore it and rerun the experiment. And then when the prisoner see HT or TH, the prisoner would decide to bring the coin. Otherwise, will not bring the coin. And of course, the guard will collect the coin and follow the rules. And then with this strategy, the chance of success is 1/3, better than the intuitive way of 1/4. Okay. Of course, smaller than if you have a prior, agreement or a collusion allowed. That would be 1/2, right? So the 1/3 is good with this constraint, right? That's a solution, all right? Hope you follow the steps and please like, share, and subscribe to the channel. Thank you.